We're kicking things off today with an idea that has long captured our imagination, often sounds like something straight out of science fiction.
Hmm.
This notion that merely observing something in the quantum world fundamentally changes it.
Right.
It makes you wonder, doesn't it? Is it really us, like our consciousness doing the observing, or is there something far more subtle and physical at play?
It's a truly captivating starting point, yeah.
Yeah.
And it cuts right to the core of one of the most persistent misunderstandings in all of physics, I think.
Precisely. So today we're taking a deep exploration into this fascinating and, let's be honest, often misconstrued concept of the observer in quantum physics.
Okay.
And for this particular journey, we're drawing our insights from a single yet remarkably comprehensive source.
Yeah.
It's an excerpt from Wikipedia focused specifically on observer quantum physics.
Right, a focused source. And our goal here is really to unpack what observer truly signifies in this context.
Yeah, and maybe dismantle some of those stubborn misconceptions that tend to circulate.
Exactly. And explore the profound implications for how we understand reality and the very act of measurement.
Hopefully, this exploration will offer you a kind of shortcut to genuinely being well-informed on this captivating subject.
Let's hope so.
Okay, let's jump right into the heart of it then. The observer in quantum physics. It's inextricably linked to what's called the observer effect. Now, this isn't about some mysterious psychic power or, having to actually see something with your eyes. What does it actually mean?
Well, what's crucial to understand here, I think, is that the observer effect simply means that any measurement, just by its very nature, requires an interaction with the physical object being measured.
And an interaction. Okay.
Yeah. And that interaction, in turn, inevitably affects the object's properties. So it's really not about conscious observation in the human sense, but about a tangible physical interaction taking place.
Ah, okay. So it's less about who or what is doing the measuring, maybe, and more about the fundamental act of measurement itself.
That's a great way to put it.
And there's even a very specific technical term for what's being measured in this context, isn't there?
Yes, exactly. We use the term observable.
Observable.
Right. In the precise language of quantum mechanics, an observable denotes something called a Hermitian operator.
Okay, Hermitian operator. Sounds technical.
It is a bit, but you can think of it as a mathematical instruction or like a rule. It tells you how to measure a specific property of a quantum system. Maybe its position or its momentum.
Got it.
And crucially, what the possible outcomes of that measurement could be. It's a very specific mathematical construct, though, not a physical object itself.
Right, not the thing itself, but the potential measurement. Okay. That brings us to what many physicists consider, well, the most contentious issue at the core of quantum mechanics. The problem of measurement and something called wave function collapse.
Yes, the measurement problem.
Why is measurement such a lightning rod for debate in quantum theory?
Well, if we connect this to the bigger picture, the theoretical foundation of measurement is indeed one of the most debated issues. It really underpins nearly every interpretation of quantum mechanics.
Wow.
And the central focus of this debate is, without a doubt, wave function collapse.
Okay, so what is wave function collapse then? Because that phrase, it conjures up images of something pretty dramatic.
It is, in its own profound way.
Yeah.
Measurement causes a discontinuous change in a quantum system's state.
Discontinuous, like a jump.
Exactly, a jump. It shifts into what's called an eigenstate of the operator associated with the quantity being measured.
A eigenstate.
Yeah, think of an eigenstate as essentially one of its definitive measurable states, like a specific value for a property, a precise spin, or energy level.
Okay.
And critically, this change is not time reversible. You
Yeah.
can't just, run the film backwards and undo it.
Right, okay. So, if a system is in superposition, meaning it exists in multiple potential states simultaneously, that whole mathematical thing, a measurement, forces it to sort of snap into just one of those possibilities. Is that the gist?
That's a perfect summary. A measurement will result in the quantum system being found in one of the possible eigenvalues. So those are the observed values of the operator.
Right.
So once you've measured the system, you know its current state. And this knowledge, which you gain through interaction, it prevents it from being in any of its other potential states.
Okay.
It is decohered, is the term, meaning it essentially settles into one specific reality, losing its quantum fuzziness and that ability to interfere with its other potential selves, so to speak.
So the type of measurement you perform actually directly affects the system's final observed state.
Precisely. What you choose to measure determines what you find.
Okay, here's where the evidence for observation's impact gets really compelling, I think, with the experimental proofs. Can you tell us about the quantum Zeno effect? That sounds amazing.
The quantum Zeno effect is truly remarkable.
Yeah.
Almost counterintuitive. It describes a quantum state that would normally decay if you just left it alone.
Okay.
But it doesn't decay simply because you're continuously observing it, or rather, interacting with it.
Wait, just by watching it?
Well, watching meaning interacting. It's as if you're holding it perpetually in place, simply by repeatedly measuring or interacting with it.
Wow.
The behavior of such a system is described by a specific mathematical framework, a quantum Stochastic master equation, the Wavefunction equation specifically.
Okay. And then there's the delayed choice quantum eraser experiment, which truly bends the mind.
Indeed. That experiment further highlights how observation, or maybe better put, the act of gaining information can impact what appears to be the system's past.
It's past. How does that work?
Well, even observing the results after the particle, say a photon,
Yeah.
has already been produced and gone through the experimental setup,
Yeah.
still seems to lead to collapsing its wave function and essentially loading a specific back history for that photon, depending on what information you gather later.
That's hard to wrap your head around. It suggests the past isn't fixed until information about it becomes available.
It certainly challenges our classical intuitions about time and causality. It's very strange stuff.
Okay, now let's tackle a major misconception head on, because I think this is where a lot of people get genuinely tripped up.
Good idea.
There's this common yet fundamentally flawed assumption that the wave function is the same thing as the physical object it describes, like thinking the wave function of an atom is the actual atom.
Right, that's a huge source of confusion.
And this often leads people to incorrectly assume some, I don't know, mysterious external mechanism, maybe something beyond physics, like a measuring instrument needing a conscious observer is needed to explain this collapse.
Yes, and this is perhaps the biggest takeaway from our dive today. If people get one thing, the truth is not a physical object. No. It doesn't have observable mass or charge or spin like an atom does.
Yeah.
Instead, it's an abstract mathematical function.
Okay, abstract function, what does it do?
Its purpose is to contain all the statistical information an observer can possibly obtain from measurements of a given system.
All the possibilities.
Exactly. Think of it like the ultimate quantum probability spreadsheet, maybe. It tells you the odds of finding the system in different states if you measure it. It's not the physical entity itself.
Okay, so if it's just a mathematical function representing potential statistical probabilities, then it changing abruptly after a measurement isn't really a physical mystery, is it?
Not in the way people often imagine.
It just means we now have concrete information instead of just a range of probabilities. It's like an update of our knowledge state.
Exactly. Perfectly put. Given that it's a mathematical representation of information, there's no inherent spooky mystery in why its form must change abruptly once a measurement has been performed and a specific outcome is known.
Our knowledge has just been updated.
Precisely. From a range of possibilities to a single observed reality. And this understanding of the wave function as information is really crucial because it helps us navigate other complex quantum puzzles too.
Like what?
Well, for instance, it's relevant to how measurements on entangled particles appear to have a non-local effect, implying instantaneous connections across vast distances.
Spooky action at a distance.
That old chestnut. And it's also why things get particularly intricate when we try to model the observer itself as a quantum system, which leads into the deeper challenges of decoherence.
Right. The observer is quantum too. Okay.
Yeah.
So if this observer effect isn't really about our consciousness, then who or what is the observer according to the sort of mainstream interpretation, like the Copenhagen interpretation?
Okay, yeah. The Copenhagen interpretation, which is still the most widely accepted view among physicists, basically posits that an observer or a measurement is merely a physical process.
Just physical.
Just physical. It has absolutely nothing to do with consciousness in the human sense. Full stop.
Von der Heisenberg, one of the founders of this whole thing, he was very clear on this. I think he said something like, the observer has, rather, only the function of registering decisions.
Decisions.
I.e. processes in space and time, and it does not matter whether the observer is an apparatus or a human being.
Right. Apparatus or human doesn't matter.
But the registration, i.e. the transition from the possible to the actual, is absolutely necessary here and cannot be omitted from the interpretation of quantum theory. So it's about a physical process making a decision or registration.
Exactly. And Niels Bohr, another key architect, further emphasized this objective character. He wrote that all unambiguous information concerning atomic objects is derived from the permanent marks.
Permanent marks,
Like
right?
as a spot on a photographic plate.
Yeah.
Something concrete and stable.
Oh, okay.
He said, the description of atomic phenomena has in these respects a perfectly objective character, in the sense that no explicit reference is made to any individual observer.
No observer needed in the description.
And that, therefore, no ambiguity is involved in the communication of information. The key is the objective, permanent record of the interaction.
Okay. And Asher Paris, another renowned quantum theorist, gave us an even more accessible analogy, didn't he? Really driving home the point that it's about physical interaction, not subjective seeing.
Yeah, Paris's analogy is great. He said observers in quantum physics are similar to the ubiquitous observers who send and receive light signals in special relativity.
Ah, like in relativity thought experiments.
Exactly. He continues, obviously this terminology does not imply the actual presence of human beings. These fictitious physicists may as well be inanimate automata that can perform all the required tasks if suitably programmed.
So a robot could be the observer. An automaton can do the job just fine, no consciousness required.
According to this view, absolutely.
This clarity, while foundational for many physicists, it doesn't entirely put an end to the philosophical debate, does it?
No, not entirely. Critics of a purely physical role for the observer often point out fascinating paradoxes, like Wigner's friend.
Wigner's friend, what's that?
It's a thought experiment where one observer performs a quantum measurement inside a closed lab, and then another observer outside the lab observes the first observer. It raises complex questions about when exactly the wave function collapses, when observer 1 makes the measurement, or only when observer 2 observes observer 1.
Whoa, okay. Observers observing observers. That gets complicated fast.
It does, and it leaves that lingering, deeply philosophical question. How much consciousness, if any, is truly required for an observation? Or is any required?
Yeah. And John Bell, a real titan in the field, he provocatively threw out this challenge, didn't he? He asked, was the wave function waiting to jump for thousands of millions of years until a single-celled living creature appeared? Or did it have to wait a little longer for some highly qualified measurer with a PhD?
Yeah.
That's a truly profound question about the very nature of quantum reality, isn't it? It challenges us to consider if reality fundamentally depends on intelligent observers.
It absolutely does. It highlights the deep philosophical implications that stretch far beyond just the physics equations themselves.
And I guess this leads us nicely to setting the record straight on some of the more, let's say, anthropocentric claims out there.
Right, the ones that pop up often.
Particularly from some New Age religious or philosophical views that really do give the observer a much more special, consciousness-dependent role, or place specific constraints on who or what can be an observer. For instance, Fritjof Capra claimed, and I'm quoting here, the crucial feature of atomic physics is that the human observer is not only necessary to observe the properties of an object, but is necessary even to define these properties.
That's a strong claim.
It is, but it's crucial to state clearly for anyone listening that there is no credible peer-reviewed research that backs such claims. The scientific consensus is firmly against that idea.
Absolutely. The physics community doesn't support that interpretation. Now, what's also fascinating and often confused with the observer effect we've been talking about is the uncertainty principle.
Yeah, good point. They sound related.
They do, and apparently even Werner Heisenberg himself, who first formulated it, sometimes blurred the lines in his explanations.
Really? Even Heisenberg?
So the history suggests. But the standard uncertainty principle describes something fundamentally different from the observer effect.
Okay, what's the difference then?
The uncertainty principle defines how precisely you can simultaneously know certain pairs of properties of a particle. The classic example is its position and momentum.
Right. Can't know both perfectly at the same time?
Exactly. If you increase the precision in measuring one quantity, like position, the precision in knowing the other, momentum necessarily decreases. It's a built-in fundamental limit to the information content of a quantum system at any given moment. It's not primarily about our act of looking causing the change, but about what's knowable at all.
So it's about fundamental limits on knowledge itself, not necessarily about our presence causing a disturbance in the act of measuring.
That's the standard understanding, yes. Now, to add a little complexity, there is an alternative formulation of the uncertainty principle, sometimes called a measurement disturbance relation, that does try to account for the disturbance an observer or measurement inevitably has on a system.
Okay.
That version is more in the spirit of the observer effect we've been discussing.
Yeah.
But it's really important to note that this is not how the term uncertainty principle is most commonly used in physics.
Got it. The main meaning is that inherent limit to simultaneous knowledge.
Correct.
Okay. So to kind of bring it all together for you listening, this exploration has hopefully shown us that the observer in quantum physics is far more subtle and, well, profoundly physical than just a conscious being simply looking at something.
Yeah, I think the insights we've extracted, especially from the mainstream interpretations like Copenhagen, make it clear that it's the physical act of measurement, the interaction, that influences the quantum system. It causes that transition from a state of possibilities, the superposition, to a definite objective reality recorded by some physical means. It's about physical processes, fundamentally not subjective consciousness.
So what does this all mean for you then, if merely interacting with a quantum system fundamentally changes it? Well, what does that imply about the very act of knowing or measuring anything in the universe, even outside the weirdness of the quantum realm?
That's a deep question.
It kind of raises an important follow-up, doesn't it? Does the act of acquiring knowledge, of measuring or observing anything, always intrinsically alter what is being known, maybe in ways we don't even usually perceive?
It certainly invites you to ponder those profound implications, doesn't it?
Right.
About the nature of reality itself and the very act of gaining information, of knowing.
Absolutely. So what stands out to you from this fascinating journey into the quantum observer? Lots to think about there.